Mr. Sutton here, bringing you the Algebra 2 11.3 lesson on analyzing geometric sequences and series. This is a two-part lesson. In part 1, we'll be writing rules for geometric sequences. We'll do a little of that in part 2 as well, along with finding sums of geometric series. And we've got a few real-life problems to put this series thing into action. Let's begin by defining what we're talking about with geometric sequences. So a geometric sequence is kind of like an arithmetic sequence, but instead of having a common difference where we're adding the same thing over and over again, with a geometric sequence, the terms have a common ratio where we're multiplying by the same number over and over again. And we can call that ratio r. So an example, we've got 2, 4, which so far looks like an arithmetic sequence, but next term is 8 and then 16. So we're multiplying by 2 over and over again here. That would be our r value for this. Now, if we graph what this looks like on Desmos, just to see, let me make a table. So let's see, we've got the n values 1, 2, 3, and 4, and we have the terms 2, 4, 8, and 16. If you do a fit on this one, and see what the shape is, this is your exponential curve going on here. So these sequences are going to follow an exponential pattern. Again, it's not an exponential function because we can't get anything in between the n values 1, 2, 3, and 4, but we can get discrete points that have at least an exponential curve to them. And with this exponential pattern, with an exponential function, you have your b value, that's your growth factor. In this case, the r is going to be the growth factor of this exponential situation. So with that in mind, we've got two sequences for you down here. See if you can figure out whether each of these is geometric with a reason to explain your decision. Give it a shot. All right, so in order to figure out if a sequence is geometric, let's look back at our definition. Geometric sequences have a common ratio. So if we find the ratio of one term to the term before it, and just keep doing that, if we keep getting the same number, that would tell us we have a geometric sequence. So we've got 12 over 6, which reduces to 2. 20 over 12, that reduces to, let's see, 10 over 6 or 5 over 3. And we could keep going, but since this ratio is already different, that means that this is not a geometric sequence because there's no common ratio. Let's try this next one. So 64 over 256, and if you don't really know what that reduces to, you could use Desmos to reduce it for you, but that is a 1 over 4 ratio. 16 over 64 is definitely 1/4. Again, you can reduce that one by 16. 4 over 16 is 1/4, and 1 over 4 is, well, 1/4. So with everything they've given us, there is a common ratio going on here. So we're going to say yes to this one because there is a common ratio. That means that this does appear to be a geometric sequence. For this next problem, they want us to write a rule for the nth term of this geometric sequence and then find the 7th term. So let's talk about a formula for the nth term of any geometric sequence. So recall that a geometric sequence has an exponential pattern. And recall what the exponential standard form looks like for an exponential function. That was y equals a times b to the x, or ab to the t, however you want to write it there. So we're going to write a geometric sequence sort of equivalent to this. So this will be a formula for the nth term of a geometric sequence. So instead of writing y, we can write a sub n, the nth term. And for our a value, with the exponential function, this was kind of like your y-intercept, your starting point. So we're going to use a sub 1 for that in these geometric sequences. Now we said that the growth factor of an exponential was basically the r of the geometric sequence. It's the thing you keep multiplying by. So b, we can just use r instead of that. And here's where things get a little bit weird. So instead of just using x, I'm going to use n minus 1 for my exponential part here. Now the reason I need this minus 1 in here, when I plug 1 into this formula, I want to get the first term of the geometric sequence. I mean, if you're promising me the nth term of a sequence and you can't even give me the first term when I plug in 1, what good is it, right? So if I plug 1 into this, I'm going to have r to the 1 minus 1, which is r to the 0, and that's going to come out to 1 overall, which means all that's going to be left is this a1 term. So I need the minus 1 to get this first term when I plug in 1. All right, so with that in mind, we're going to go ahead now and try out this problem. So whenever they say geometric sequence, a good idea to just write down this formula right off the bat. Good things will happen. And we see here that if we're actually going to finish this formula, we're going to need to figure out the values of a1 and r. So that's what we're going to do here is find and plug in a1 and r. So pause the video, try that out, and let's see what you come up with. So for a1, we can get that pretty easily. That's just the 5 here. It's the first term of the sequence, so no big deal there. For r, we have to find the common ratio. And again, we can get that just by taking one term and dividing it by the term before it. Because again, we're asking what did I have to multiply by to get from one term to the next. So if we do 15 over 5, that gives us an r value of 3. And then we can plug that into this. So I'm going to have a sub n equaling 5, that's my a1, times 3 to the n minus 1. And I don't really need to simplify this any more algebraically. It turns out this is going to be good enough for our purposes. We do, however, want to figure out the seventh term. So to do that, we can plug 7 directly in for n in this problem. And let's go ahead and use the calculator now to actually crunch those numbers. So here's my scientific calculator. I've just got 5 times 3, and let me raise that to the, and I'm going to need a parentheses here, 7 minus 1, just to put all that in the exponent. Or you could do the subtraction in your head and just call that 6. So that's going to come out to 3,645. Here's another one for you to try out. Same kind of deal as the last one. Pause the video and give this one a shot. All right, so again, we've got our exponential form, our geometric formula, a1 times r to the n minus 1. So this time around for the r, we've got negative 44 over 88. And if you don't like reducing that, again, it doesn't really matter which two terms you use as long as they're next to each other. So you could go the much easier route and do like negative 11 over 22. In any case, every time you're going to see that this comes out to negative 1/2. So we're going to have 88, my a1, times negative 1/2 to the n minus 1. And I do want to make sure I put that negative 1/2 in a parentheses there so that it all gets affected by the exponent. And then to get my seventh term, let me do 88 times negative 1/2 to the 7 minus 1. And back to the calculator here. So I'm just going to take what I had last time and replace a few things. Instead of 5, I've got 88. Instead of 3, I've got negative 1 over 2. And I still have 7 minus 1 up here, so I can recycle that. And that gives me 1.375, which I could definitely write down, or round it to the nearest 3 decimals, which it already is exact. You could also turn it into a fraction with this little button here, and that's 11 over 8 if you prefer that format. For this next problem, we're just writing the nth term of this geometric sequence. We don't have to come up with the seventh term anymore. But it is a little trickier because they're not giving us a1. They are, however, giving us the r value, so we can at least use that. So let's write our formula again. a1 times r to the n minus 1, and this time we're going to have to find a1. Now we had problems kind of like this when we were doing arithmetic sequences, and in these situations we discovered that we can plug in for the an and the n using the term that they did give us, and that will allow us to solve for that missing a1 value that we need to complete the problem. So with that hint in mind, pause the video and give it a shot. All right, so I'm going to replace this a sub n with 12, the value of a4. And then for a1, I'm still looking for that. For r, I've got 2. And then for n, I have to use 4 because 12 is the fourth term. So we have 4 minus 1 up there. So this is 2 to the third, which is 8. And if I divide by both sides by 8 to get a1 by itself, 12 over 8, I can reduce that to 3/2 if I like. So plugging that back in, we have a sub n equals 3/2 times 2 to the n minus 1. So this is the end of part 1 of this lesson. Hopefully things are still going well. Pause the video and try out some problems of the types that we've been dealing with here, and then we'll bring it back for part 2, where we take a look at some more nth term kind of stuff, tougher problems, and also some geometric series and applications. Welcome back for part 2 of our lesson on geometric sequences and series. To kick this one off, we're going to be asked to write a rule for the nth term of this geometric sequence. Now, just to make our lives a little bit tougher, notice that they are not giving us consecutive terms. They don't give us a1, so we're going to have to find that just like before. But also, we have the second and the fifth term. So unfortunately, if I was looking for the r value, which I usually do right away, I can't just divide a5 by a2. Because that's not going to give me what I need to multiply by to get the next term. That's going to give me what I need to multiply by to go 3 terms ahead. So in order to handle this situation, I've got a little formula that I cooked up to help us out with this sort of thing. So we do need to actually divide these 2 terms together. But with the number that we get out of that, we're going to have to take a root of that number in order to figure out what I'm multiplying by to get each individual term ahead. And what root is it going to be? Well, that's going to depend on how far apart these 2 terms are, how many times I have to multiply by the same thing. So here's my formula that takes that intuition and kind of puts it all together. So I'm going to say that r equals the m minus n root of a sub n over a sub n. So basically divide these, subtract the indices, take that root, and that should give us the actual r value that we would have to multiply by to get from 12 to negative 768 in this many steps. So pause the video, apply that, and then see if you can work backwards to get everything else you need to write the nth term of this thing. Good luck. All right, so let me try this out here. We're going to have 5 minus 2 root of negative 768 over 12. That's what this is all amounting to here. And let me see what negative 768 over 12 is. I mean, I could just plug this whole thing directly into the calculator, but I don't need to do that. Let's just take it in steps here. So negative 768 divided by 12 comes out to negative 64, and 5 minus 2 is 3. So I have cube root of negative 64. Now you might know just kind of in your head that I have to multiply negative 4 times itself, 3 of them, in order to get negative 64. And if you got that, that's great. Just to review on the calculator, if you needed to, you can figure this out by doing, for third root, you can do cube root, CBRT, and that's a special one. If you just want to do the nth root, you just write nth root, and then we would put a 3 up here, a negative 64 in here, and that would do it for us as well. All right, so we've got the r value. Now I'm going to write my geometric nth term formula, right? Because we're eventually going to have to plug r into this thing. We do still need to find that a1 though. So just like we did back in example 4, we're going to plug in the r value and one of these terms with its index to solve backwards for that a1 value. So I'm going to use the second one because that seems way easier than using this other crazy thing here. So for my a sub n, I've got 12. My a1 I'm looking for, r we just found is negative 4, and I'll put that in the parentheses. And then n, since I'm using 12, I have to use the 2 index for the n value. So 2 minus 1. 2 minus 1 is just 1, so this is just negative 4 times a1. Dividing to get a1, I have negative 3 for that. And now I've got everything I need to plug everything back in. So I can write a sub n equals negative 3 times negative 4 to the n minus 1. Whew, made it. For our next topic, we're going to be finding the sum of this series. Now, this isn't just any old series. It turns out, because of this exponential term in here, you might recognize this as kind of like the nth term of a geometric sequence. That makes this a geometric series. And that's how you can recognize it's a geometric series, by just looking to see if there's an exponential sort of term in there. Or you could start plugging in these k values and seeing that we keep multiplying by 3 over and over again. In any case, how do I quickly find the sum of this thing? Well, it turns out there's a formula just like for the arithmetic series. So here is the sum of a geometric series. The sum of the first n terms, s sub n, is going to equal a sub 1 times 1 minus r to the n all over 1 minus r. So to use this formula, we need the first term, we need the common ratio, and we need the number of terms. This is a little bit different from the arithmetic formula where you might remember we also, for that one, we actually didn't need the common difference for that one, but we did need the last term. This one, kind of a different setup. And if you're wondering where this formula comes from, there is a quick 4 to 5 step sort of derivation of it, which you can quickly find online or on a YouTube video, but it's not very helpful for actually using it, so I'll leave you to check that out on your own if you're curious. But we're going to use it. So you actually have everything you need here based on what you've learned so far to try this out. So pause the video and give this thing a test drive. All right, in order to make this work, we need to figure out the n, the a1, and the r values, and I'm going to find them in that order. So n, again, if your first term is 1 here, that means your upper limit of summation is going to be the number of terms. If this first k or I value here is not 1, then you'll have to adjust and count accordingly. So we've got n of 10. A1 is what I'm going to get when I plug 1, or whatever my first index is, into the summand. So we have 4 times 3 to the 1 minus 1. That's 4 times 3 to the 0. 3 to the 0 is 1, so that's just 4. And then we've also got the r value. That's what we keep multiplying by over and over again. And to figure that out, you could just notice that, hey, 3 is being raised to the exponent, so that's what I'm multiplying by over and over again, and write 3 for r. Or you could plug in 2, get another term, and then divide term number 2 by term number 1, and that would verify that indeed 3 is the common ratio. So plugging all this in, the sum of our first 10 terms, we're going to have our a1 of 4 times 1 minus r, so 1 minus 3 to the 10th power, all of that over 1 minus the r value 3. And for this, just because of the size of the numbers involved, most of the time we are going to need to use some kind of calculator in order to get the final answer. So let's go to Desmos for that. So let's make a fraction here, and we've got 4, parentheses, 1 minus 3, exponent 10, close that parentheses, and then go down to the denominator where we've got 1 minus 3, and that comes out to 118,096. For our next problem, we're going to use some of what we've learned in a somewhat real-life setting here. This is at least plausible for a real-life problem. So let's say you post a meme on your social network page. I could see somebody doing that. Maybe it's this one. I would post this one. If you don't study, you shall not pass. It's tough luck for the Balrog, I guess. So anyway, let's say that 6 of your friends repost the meme, and then 6 of each of their friends repost the meme, and so on. And, you know, just to kind of fit this into an easy to make a math problem thing, we'll say it's exactly 6 each time, even though in real life that's probably not going to hold true consistently. So what we want to do is find the total number of people who reposted the meme after the 7th round. Well, if 6 of your friends reposted and 6 of them, of each of their friends reposted, we're essentially multiplying by 6 each time. So this is a geometric kind of setup. So with that in mind, pause the video and see if you can figure out how many have reposted this after round 7. All right, so since this is a geometric setup, probably a good idea to use our geometric sum formula, a1 times 1 minus r to the n over 1 minus r. And now let's just find the different pieces of this. For n, they said 7th round, so we'll let n equal 7. A1 is going to be the 6 of your friends that reposted the meme, so that'll be 6. And then for the r value, well, we're multiplying by 6 each round, so that's also 6. So we end up with 6 parentheses 1 minus 6 to the 7, all over 1 minus 6. And then let's just put this in Desmos. And I'm just going to piggyback off of what I had for my last entry. So I'm going to replace that 4 with a 6. And I've got 1 minus 6 to the 7, all over 1 minus 6. Easy to change all that. And wow, so after round 7, that is 335,922 people. The power of exponential growth. For our last problem, we're going to use this formula here to calculate the monthly payment on a loan. The way that this formula is set up, L is the loan amount. This I right here is the monthly interest rate in decimal form. And then the T, that's the upper limit of summation in this summation in the denominator here, this is the term in months. This is in months again, so be careful with that, because if they give you something in years, you're going to have to convert that. So what they want us to do is calculate the monthly payment on a 5-year loan for $20,000 with an annual interest rate of 6%. The only other little tricky thing here is if you have an annual interest rate and you need to get a monthly interest rate to use this formula, you're going to have to convert that. So you can get your monthly rate by dividing the annual rate by 12, which makes sense. So with all that in mind, pause the video and see if you can plug the right numbers in the right places. Oh, and you're going to have to use the Desmos graphing calculator in order to use the summation notation. To get that on the Desmos grapher, you just have to write SUM, sum. So pause the video, give it a shot. All right, let me first get that monthly interest rate I, so I don't forget to do it later. So we are going to have 0.06 divided by 12. And let me just run that on the calculator. And I've got my Desmos grapher out because I'm going to need it anyway. So 0.06 divided by 12 comes out to 0.005. All right. So plugging some things in. For our loan amount, L, we've got 20,000 for that. And now for my summation, K is just K. We just use that as our index variable here. But this T I actually have to replace with something. Again, this was the term, how long the loan was for in months. Since it's a 5-year loan, we need 5 times 12, or 60, for that upper limit of summation. And now in this parentheses, the I is going to get replaced with this 0.005. So we have 1 over 1 plus all that. And the K we're just leaving in there, again, because we need it for this summation. So let's plug all of this into Desmos now. Let me move that a little bit so I can see. All right. So I have a fraction. We have 20,000 in the numerator. In the denominator, I'm going to need SUM. And I'm going to have to use N instead of K. So we have N equals 1 to 60. And then my summand, I'm going to put that in a parentheses here. So we have a fraction. We have 1 in the top. In the bottom, 1 plus 0.005. Close the parentheses and exponent that to the, we're going to have to use the N power because, again, that's equivalent to K here. So this is what it all comes out to, about $386.66, which seems kind of reasonable. Doesn't seem super crazy. So there we are. So this concludes our lesson on geometric sequences in series. Thank you for lending me your time and your ears. Until next time, Mr. Sutton signing off.